this video, I want to show you how to write microcode that will accomplish tasks in our processor circuit. Keep in mind that the ultimate goal here is to do nothing more than to move bits around in our processor in order to accomplish some job. I like to think of it almost like moving cattle around on the old west on a ranch someplace. And imagine that you had to move the cattle from one pen to the other, and that there are 3 different gates that you can open and close, various pins you can go through along the way, but only 3 gates that you can open and close. Well, this processor circuit has 3 controlling gates, and if you can set those gates properly and then clock the circuit, the bits will move wherever it is you want them to move. Let's get started. Let me first point out the 3 gates that we have to work with. The first one is this multiplexer on the main circuit. Now the multiplexer determines which of these 3 devices, the arithmetic logic unit, the general register, our load immediate port, there's a 4th device here, a constant 0, which of these devices is going to output their signal onto the data bus. That's the job of this data bus controller. It's a multiplexer. The second gate that we have to work with is down in a register subcircuit. So I'll open up the registers. And there's actually 2 controlling devices here. The first one is a register select. It's a decoder that selects which of these 4 registers is going to be active to receive the data coming in from the data bus. The second signal here is a multiplexer that determines which of these registers will send its signal to the data bus. So we have the 2 controllers here. Now the way this works is that on this input controlling signal, 2 bits will be used to determine which of the registers are active. And those 2 bits are fed to both the decoder and the multiplexer. The 3rd bit is used to activate or inactivate either the decoder or the multiplexer. If the decoder is active, then whatever signal is coming in off of the data bus will be fed to one of the selected registers. But if the output multiplexer is active, then whatever signal is, the selected register will feed its contents out to the data bus. The 3rd controlling signal that we have controls the arithmetic logic unit. The arithmetic logic unit signal is a 4-bit signal. Now 1 bit is used to do nothing more than select whether the input buffer is going to be active or whether the output accumulator is going to be active. If the input buffer is active, then whatever's on the data bus will come into the arithmetic logic unit. If the output accumulator is active, then whatever is in that accumulator will be fed out to the data bus. The other 3 bits that come into the arithmetic logic unit are used to determine which of these functions are going to be active. So let's see how this works in practice. Suppose that my goal is to take some value from the load immediate register and move that value into register 0. I'm going to start by putting some value in load immediate, and it doesn't matter what I put in there. For testing, I usually just put 2 in there. And I want to move this value to the register. So the first thing I know I have to do is set the data bus controller multiplexer so that this input, the load immediate input, and that's input 2. Remember, we start counting with 0, so 0, 1, 2. So I want input 2 from this multiplexer to be fed out to the data bus so that can go into the register circuit. All right, here's how that works. I'm going to have a 9-bit microcode input. And let's take a quick look at the control circuit. This 9-bit input controller, or 9-bit input signal, will be split into 3 different outputs. 4 of those bits will control the arithmetic logic unit, and it turns out those are the 4 low order bits. The next 3 bits will control the registers, and the high order bits will control the data bus. Oh, for instance, if I had an input signal something like this, then those high order bits would control the arithmetic logic unit. The next 3 bits would control the register, and the 2 highest order bits would control the data bus. So I know that in order to move, and here's my goal, I don't think I mentioned this goal, I want to move something from the load immediate register to R0. Now we abbreviate that by doing something like this. So load immediate will be moved to register 0. This is what we want to do. Let me just kind of move this over here out of the way. So I know that load immediate register needs to be on the data bus. And in order to do that, those load immediate bits, the data bus controller bits, those first 2 bits in our microcode need to be set for 2. And of course, in digital logic, 2 is 1, 0. So those first 2 bits, I said 1, 0 and I typed 0, 1. Those first 2 bits need to be 1, 0. Now that 2 bits, those 2 bits, will in fact put the contents of load immediate onto our data bus so that can go into the general register. So the next thing I have to wonder is, in the general register subcircuit, what do I need to do in order to load that number into register 0? And let's take another look at the general register subcircuit. The way this subcircuit works, with the input signal, the controlling signal coming in, it's divided into 2 parts. There's a 3-bit signal, I know that, but it's divided into 2 parts. And it's the 2 low order bits. I've got this backwards, so let me just change that. I don't want to confuse anyone. The 2 low order bits, these 2 bits, are used to determine which of the registers are going to be active. All right. Since I want to move load immediate into register 0, then these 2 bits need to be set for 0, just like I've illustrated here. That high order bit from the controlling signal is used to determine whether the registers are going to be loaded from the data bus or whether they're going to read their value out to the data bus. So that high order bit in this case needs to be 1. Because 1 will turn on the decoder, which will permit the data input from the data bus to go into register 0. With that 1 set, that signal is changed into a low, feeding that output mux, which deactivates the output mux. So nothing going on inside this register circuit is going to be fed to the outputs. And that's what we want in this case. So I know that that next group of 3 needs to be 1, 0, 0. Finally, we have the ALU, the arithmetic logic unit. Now, in this particular instance, nothing is going on in the arithmetic logic unit. It's out of this circuit altogether. So those last 4 bits can remain at 0, 0, 0, 0. Now, I've already put 2 in the load immediate register. So let me do this. I'm going to set up my microcode. I said I wanted a 1, 0. The next 3 bits should be 1, 0, 0, and the last 4 bits are all 0. If I clock this circuit and then go take a look at the registers, I would expect register 0 to now contain a 2. And to look at the registers, I don't want to just click on the register because that puts me in the design view. Well, let me just show you. And you can't really see what's happened in here because you're designing this. Instead, what I want to do is click this second button, and this shows the simulator in operation. Now if I go out to the registers, I can see that register 0 does indeed have a 2 in that register. Let me go back to the design mode and back to the main circuit. So to figure out how to write microcode, just remember you only have 3 devices you can control, and you need to figure out how to move bits from one spot in this circuit to the other, and what you're going to do with those bits once you get there. I know it's challenging. Good luck with it. I'll be seeing you online.